Okay, good.
I'm gonna share my screen right now.
Hello, team. Good afternoon, or good morning, I should say, for you.
Hi, good morning, everyone.
Good morning.
Good morning.
Good morning. So we're Team 18 from Thailand, Chulalongkorn University High Altitude Research Club. So today we will be having a virtual review on our Cursor 3 rocket in the 30K COTS category.
Okay.
Okay, so I'm gonna start with the flight dynamics team. So here's our layout of our rocket in OpenRocket software. We have three main airframes, start from the booster, the drop parachute, avionics, and the nose cone. So the configuration and the placement of all components are shown here in the figure. This year we added both tail and a new camera shroud, including the new design fin in this design as well. Here's the result of our data from OpenRocket. So from the last year that we experienced wind condition and environmental condition, we decided to do simulation in from 6 to 9 meters per second for wind speed. And here's below is the graph of the flight profile, the altitude, velocity, and acceleration of the rocket. And we also use RAS Arrow as another software because as we revealed, a rocket is not entirely accurate, especially during the supersonic regime. So we use RAS Arrow as another software, but there are some limitations like the shape of the boat tail. So we also include another software, which is Rocket Pi. It's a
All right.
Python-based library simulation software. We did a Monte Carlo simulation of 10,000 iterations. And here's the graph that we have. We have the apogee of 9,000 meters, which is about 29,750 feet. And they're also a result of the maximum velocity of 572 meters per second and maximum acceleration. So from the RAS arrow that we choose, because it can include the environmental data of the launch site as well. It can import the real-time data, the forecasted data that we will use prior to the competition, and we can compare the result to OpenRocket RAS and RAS arrow to verify the simulation result. And here's the simulation results from three software, OpenRocket, RAS arrow, Rocket Pi. We found that all software have equal result with some slightly difference, which we believe is from drag that some software may not calculate it correctly. And here's a fin factor analysis that we obtained the equations from NACA 4197, and we did some research, and we found some modification of the equation from Apogee newsletter. And here's the CFD.
Okay, so we also do a CFD simulation to analyze the supersonic flow around our rocket. we found the drag force to be maximum about 939 Newton. And so here are the results of the dynamic pressure control. We also do a CFD on some certain components about the camera shroud and also the fin.
And for the fin, we have ran a CFD on at Mach 1.7, and this is the contour of the static pressure. And this is the contour of the static pressure on the fin. And we also opted for a hybrid OGIF, which is a blend of a secant and tangent OGIF on the rockets as well.
So for the rocket design, we use the commercial off-the-shelf fiberglass airframe from the Wyman rocketry and carbon fiber booster section from Wyman as well. So we use G12 fiberglass airframe. And our commercial design is 45-degree from the fins. So the turbulence will not affect that much on the fins. And the booster section, we feature the bracket and fin. So we can replace the fin if the wind velocity is higher, something like that. So for the airframe cutting, we use the bandsaw machine to cut the airframe, and then we mount the surface and we sand the surface on the jig, and we have the fiberglass sheet, which is very fat, so the airframe will be fat. So this is the final result of our airframe. So we have two lengths of the airframe. One is for the main parachute bay, and another one is for avionics and door chute bay. So
And the shape for our nose cone is one comment, and we have to enlarge the nose nose cone tip because last year the thread length inside was completely stripped, so we increased the diameter from M6 to M8 to increase strength.
next for our payload bay design, this year we integrate the payload into the nose cone. So it will be harder, but it can also doing a lot more to integrate the payload. So in this case, we use the M8 eyebolt at the top of the nose cone to the nose cone tip, and then we use the two M6 stud running along the carbon fiber thread, sorry, and then we have the top and the bottom payload bulkhead, which is slot into the payload shape, which is TU. So we also have centering box, which will be screw by radius screw, and then we have the M10 eyeball at the bottom, so we can have the main parachute at this section. So here
Okay,
is
one
the
quick
side-
question.
Okay.
Are your what are your bulkheads made out of? Are they carbon fiber?
Yes, all the bulkheads in the payload will be carbon fiber.
Okay. Okay, keep going.
Okay, we will use CNC machine to cut the carbon fiber sheet. Okay.
And for the camera shroud slot, we'll use the manual milling machine to cut out a portion of the airframe. So in the end, it's supposed to be the camera shroud is supposed to sit on the airframe and stay flush with the airframe.
So here is the assembly of the camera shroud and the airframe. And next, we do the camera shroud. We use the camera shroud mold from 3D print, like 3D pieces camera shroud mold, and then we do sport carbon. So the camera shroud will be used 0.04 chopped carbon fiber with the resin with the epoxy resin. So the final result will be fit with Lancam with 4. So we have here.
Okay, next is the booster airframe. There will be three components. First is the main booster airframe. Then there's 4 fins and 4 brackets. The assembly process works like this. First, you insert the bracket in the internal part of the booster airframe, and then you secure it with 8 M4 bolts on each side. And then you insert the fin on the top of the bracket and secure it by 6 M4 bolts. And by doing this, we have to slot mill the booster airframe. We'll be using the milling machine. And the dimensions of the slot mill we'll be using I mean the slot is 7.48 inches in length and 0.39 inches in width. That would match the dimensions of the bracket. And we'll be purchasing the booster airframe from Wildman Rocketry. It will be carbon fiber. And next is the fin and bracket designs. The fin dimensions and features are the leading edge would be 1.063 inches this time, and the length would be elongated to 9.84 inches. The height would be slightly taller at 4.134 inches, with an additional tap height of 0.551 inches. The bracket dimensions and features this time, there'll be a chamfer on the side of the bracket, as you can see from here, 0.0939 inches, as well as 6 holes to lock the fin in place, and 8 holes this time to lock the bracket with the airframe. The material we'll be using for both is aluminum 7075 T651. And we'll be manufacturing the fins and bracket using an outsourced 3-axis CNC machine.
Okay. The next
Okay,
is the
just
thrust
one quick question here on the on your I know you haven't talked about your boat tail yet, but the you said your fins were replaceable, you know, built to be replaceable if needed. How about your boat tail? That's you know, since that's the part that hits the ground first that tends to get dinged up, is that readily replaceable? Or if it just gets dinged up, it gets dinged up?
It will be replaceable. So we will have we will present next about the thrust plate and boat tail. So we will have 2 set of thrust plate and boat tail for each set of composite.
Okay, okay.
Can you present next?
Okay. So now I'm going to talk about the thrust plate design. Today we decided to merge the flange retainer and the thrust plate into one piece. The reason is that the addition of the bow tail required that the motor would be a bit lower than usual. So the old flange retainer, the cut one, would not work. So we decided to integrate into one piece. If you can see, there are 2 rows of M4 bolts. The upper one is used to connect the thrust plate to the airframe, and the lower rows are used to connect with the bow tail. And the thrust plate link, a ring and the thrust plate are all using like a custom thread. Here, the thrust plate main function is to carry the load from the motor. So it's essential that we determine and iterate the design based on the structural integrity. So as you can see from the FEA analysis, we used the overperformed data from the last year of this motor, and we found that this design is perfectly strong. The safety factor is off the chart here. The material we are using is the aluminum 7 or 75, which is very strong. Here is the boat tail that you asked for. This year design, the boat tail we use, it has the ogive shape on the upper half and the conical shape on the lower half. And you can see at the upper half, there is also a cylindrical portion extended from that ogive area that would slide into the thrust plate. And we are opted to use resin infusion process for making the boat tail this year. And the resin infusion process, it offers very high strength to weight ratio. But boat tail outer profile is the most important. So it's very logical for us to use the female mold to make it. But to make the female mold, we have this 3D printed plug that we printed first, and then we use that one to make the mold, as you can see, the pink one on the background. And then we use infusion to make the boat tail. And then after trimming, we got a completed one like this. Okay.
Next is the avionic bowhead. So avionic bowhead is made by 0.2-inch thick G10 fiberglass plate assembled with the screw. The maximum diameter is about 5 inches with fitting the airframe, while the inner plate has the minimum diameter about 4.6 approximately, attached with the cover for the section of the O-ring, and they're secured by using stud and nut to prevent the vibration. Each ball head has 2D subconnector for ejection system, and both ball head also hold quad eco CO2 system and eye bolt for chute attachment. And moreover, the top ball head also have the section to insert the cameras.
This is the avionic bay of facility is constructed by 3D print ABS plastic because of temperature resistant and radio transparent property. The avionic bay is divided into two sections, the top and the bottom, separated by a bulkhead, which are joined together by M8 steel stud. Top section is mainly made to protect flight operating components, which are divided to the fixed part that's used to attach the PCB and the battery holder, and the hinge part that's used to attach Telemica board and GPS module. Bottom section made to attach camera controller section and battery holder.
And next,
Okay, yeah, quick question. Let's go back to your avionics bay. Yeah, so what material are you using to 3D print your avionics sled?
We use ABS
ABS
plastic.
Oh, ABS. Okay, good. And yeah, so that obviates a lot of the questions. The reason I check this is because in the past, when I've done post-flight data recovery, I've had more than one rocket with a 3D printed avionics bay that when you open the thing up, it just came out in pieces because it, wasn't stressed enough to handle the vibration, or, they didn't, choose the right infill or the right material. But ABS should work well. So, okay, good on you.
Yeah,
Okay,
last year
continue.
we also used this material, so I think it would be work for this.
Okay, very good.
and for the booster bulkhead, we'll be making this from a carbon fiber sheet that has 0.4 inches thick. We'll be using our own 3-axis CNC machine to mill this. The bulkhead has an ISO grade feature to save some weight, and we will secure this to the forward closure of the motor.
So for the second ring, we use to secure the motor, like the motor tube in the place. So we just put it in an epoxy on the motor tube. This year we use like the fiberglass reinforced motor tube. Okay, so here is our rocket static structural simulation. So in this year we can see that the total deformation is very low and the safety factor is quite consisting of 3 gigapascal of the fiberglass airframe. So here is the most safe part is on the camera shell screw.
Okay, so moving on to the ejection component, the SRAD component. So it's called DODO, which is short for dual order detonating operation. And how it works is basically it uses a small amount of black powder, and the ignition upon it causes pressure to push the pin and create a hole in the CO2 cartridge and causing the CO2 to dissipate, as you can see in the picture. So in terms of the bulkhead simulation, and for this one, the indicator is indicating safety factor. And as you can see that there's 2 holes, which has a bit of a red tint to it. And we'll resolve that by using washers, which will help distribute the stress more evenly. So it won't be a major issue. And here it's a displacement indicator. So as you can see, the maximum displacement is 0.186 millimeters. So not much of deformation, major crisis over here.
Okay, as for the deployment configuration, we utilize dual deployment, which is the booster section is connected to the 30-inch drop parachute by the 3 feet and 3 feet nylon shock cord and 20 feet nylon shock cord to the bottom of the avionics part, and the 120-inch main parachute is connected to the top of the avionics bulkhead by the 20 feet nylon shock cord and the 3 feet to the bottoms of the payload section. Okay. And here we did check the safety factor for the maximum expected load to the rated maximum load and found out that the safety factor is good.
Okay.
So next is the avionics. So for flight computer, we will use the so both SRAT and the cloud system. So for SRAT, we have sensor like the IMU, barometer, and the GPS, and also the accelerometer. And for the radio transmitter, we use LoRa. And for the COTS, we use the telemeter. So this is the our SRAT. So for LoRa, we use 915 megahertz with 1 watt of power.
So our SRAT flight computer will be powered by lithium-ion battery and directly connected to our Dodo ejection systems. Similarly, our telemeter will be connected to the repo and commercial off-the-shelf even CO2 ejection systems. Both auto systems were completely independent and only activate if only the turnkey turn on. So we already finalized the battery that we will use in our rocket. We use the Panasonic lithium-ion and the lithium polymer from Wagner Rocketeers, which work very well in our color tool last years.
So the camera system is about to rig three unit of Runcam Spitfall, which is going to connect with SRAT camera controller, which for processing and signal selection, for sending the analog video signal to the VTX. The camera controller is connected with flight controller, which going to switching the signal about to select the camera, which going to send the signal to the ground station using UART0 communication. And the configurations is not decided yet. And this is the completed upper avionics bay.
All right, so for our payload, this year we're creating a gimbal that essentially rotates a LoRa transmitter so that it always faces the ground station. And here is the design. It's made of aluminum, and it will be made using our in-house CNC machine. The sensor is rotated by 3 small micro brushless DC motors, and at the center is all the electronics that we will have on the gimbals, the LoRa, and IMU and an antenna.
So we already have like main electrical components with us, like simple the ESC, the motors, and those are microcontroller and sensors. And we are currently now in the process of manufacturing and coding.
And that's everything.
Okay.
Okay, for the first and second progress reports feedbacks, we don't really have anything that you guys comment on. So this is it for our virtual progress review.
Yeah. Yeah, no, your first, I was a reviewer on your first 2 progress reports, and they all looked pretty good. You've solved the problem of your of the high altitude separation, because I know you had initially thought about using black powder, so the switch to CO2 is good. Who's your flyer record? Is that
Julian?
Yep, that's me.
Oh, okay, gotcha. All right, just wanted to make sure that you were here, and I saw your comment about the quick links, and it's probably not a bad idea. Let's see. For your for the points where you're going to separate the airframe, are you using what, shear pins to hold those together until you fire your ejection charges?
We are using M3 cheer pins.
Okay. How many are you using? What, 2 or 3?
4.
4. Okay. Okay. And have you and I saw you did the test of the dodo device. Have you done a separation test on the on the system yet?
Yes.
Okay, and that was good? Take it?
Yes.
Okay, all right. I'll take your word for it. So from what your presentation, I gather you don't have your rocket in, even semi-final form yet. Am I reading that correctly?
We have all of the airframe cut and sanded. We're just waiting to put some paint on and drill them. Also, parts such as fin, thrust plate are being manufactured right now. We're
Okay.
sorry that they're not done yet because we actually plan on having the virtual progress review like a bit later than today, but it's all good because they're all in the they're all being manufactured right now, so it's fine. Yeah.
Okay, so let's plan on doing this, and what you have so far looks really good. I see no showstoppers here, but I do have some availability on the 19th, which would be the Sunday, the last day, because I'm traveling internationally. I won't be back till about midnight the night before, but
Oh, yeah.
I do want to see your rocket. So if maybe we could just set up like 50. I'm assuming you'll have it done by the 19th, or largely done by the 19th. So if we can just set up like a 15-minute call, and we'll work out a time, and I'll just so I can lay eyes on your rocket and and feel like you've got it all together. I'm not terribly worried about that front. You've got a good track record, but we are being asked to actually lay eyes on the rocket. So that's so let's circle back on Sunday on the 19th, just to just so you can show it to me, and I'll ask any questions that are raised at the time. One question that I did have though, and
Okay.
that was prompted in the chat, was your rail buttons. What are you planning? How are you planning to do your rail buttons, and how are you planning to attach them?
Okay, for the rail button, we place 2 rail buttons. One is that at the very rear of the rocket, and one at the CG of the rocket.
Okay. And
And
okay.
What are they being fastened to? Is it just on the skin, I mean on the carbon fiber part, or are you mounting them into some of your retainers or any aluminum?
Yeah.
Are you threading the aluminum and attaching the rail buttons there?
So we have a thread insert inside. So we use the bar thread insert and mount it with the epoxy. So it will be secure like that.
Okay, so in between that nut plate and the rail button, it's just the tube.
Yes.
Okay. Yeah, just make sure it's strong enough to hold the weight of the entire rocket, even without a support structure underneath. So really that last rail button, the aftermost rail button, has to have a really strong connection.
Okay. So we will ensure that.
Yeah. That's the because we occasionally have had problems, and we did have a issue last year where a gust of wind, which we get, and any of you been out to the spaceport before know that wind's a factor. They had a gust of wind, basically caused the rail button to separate while the rocket was still on the launcher, and it actually ended up given somebody a pretty good bruise when it hit him. Unfortunately, no more damage than that. But yeah, that especially as rail buttons really need to be locked in there good.
Are you using the airfoil rail buttons or like the regular ones from Apogee?
The regular one.
You say it again?
The regular ones from Apogee.
Yeah, I don't know if I already told you this, but I forgot where I got them or where the Malaysian team got them from last year, but one of the rail button products out there are pretty flexible, and in the heat of the sun, you know, those guys, I think they over torqued the screws and it actually kind of squished the rail buttons, and they didn't know about it until it was actually time to load the rocket on the rail. And so the rail buttons were squished and it wouldn't actually enter the rail. But
Wow.
thankfully some of the guys out there, they had extra rail buttons, so we quickly swapped them out. But it's just something to look out for.
Yeah, no, that's a good put. And we will have a length of rail out there in or near the team area, so that you can test fit your rocket onto that and make sure that you don't have any similar issues. So that should help. Okay, your motor. What kind of motor do you have, and do you have it, and how are you planning on getting it?
Okay, so we use O5500 Aerotech motor. We have already purchased the motor, and we will get it when we add the last cruises.
Okay, so you've already got it purchased and set up for set to deliver.
Yes.
Okay, good.
So we have some parts done. Would you guys like to see those parts?
Which part specifically?
The airframes and avionics bay, camera shroud, and boat tail.
Yeah, no, I've seen enough of that. I want to see the rocket in basically assembled. But I've seen enough from your graphics that I don't have any concerns about those specific issues. Okay. Okay, we talked about this year. Okay. Joanne, you got any other questions or comments that you'd like to make?
Not at the moment, but you know, anything up, we have a group chat, and I bring up any of my concerns there, and these guys are fairly responsive.
Okay, yeah, no, that's we will take care of that. How many of the team have been out to the spaceport before?
This year there will be 20 people in our team, and about 10 of us have been to Spaceport before in SAC 2023.
Okay, so you know what the what the environment is like. You know, it's really brutally hot out there. Dressing appropriately is pretty important. You'll see me out there wearing long pants and a long sleeve, lightweight fishing shirt and along with a big floppy hat to keep me from getting fried in the sun, which is very, very easy for me, unfortunately. But if and I live here, and I live just about an hour south of the spaceport, so this is the environment I'm in all the time. So for those who haven't been there, resist the urge to wear as little as possible. There's lots of pretty much all the plants have some kind of thorn or spine on them. So again, long pants is going to keep you from getting scratched up. So I would make sure that you've got everything, that you've got hats, sunglasses, sunscreen, enough of that for everybody. Okay, we will have a water buffalo, the truck with a big tank of water on it. But you should plan to bring your own, good tasting water and whatever snacks or lunch that you think you need. So you've got your flight arrangements made and your hotel room or Airbnb booked already.
Yes, we have 2 Airbnb booked for to accommodate our team.
Okay, very good. Let's see. Are you planning to ship anything to
No, we're
to
not
to
shipping
the
anything, but some parts will be carried by us when we're flying to the US.
Okay.
Yeah.
Okay, good. I just wanted to make sure because we've got the convention center is accepting deliveries and it just, if you were going to ship anything, I was going to I was going to go through those details, but we don't need it. Visas, how are we doing for visas for everybody?
All 23 of us have got our visa.
Excellent.
Yes.
Excellent. That's very, very good. Okay. Stan, most of you, at least those of you who are going to be downrange, all are EEE members at least at the student level. Just want to
Yep,
confirm
we all
that.
got it.
Okay, very good. And are you planning to are you transmitting on a frequency where you are going to need a ham amateur radio license for the States? I know you're using LoRa, but if you were going to be, on the 2 centimeter band or whatever for your GPS.
Most of us have got a ham license.
Okay.
Yeah.
All right. Not a problem. So just as a reminder, you'll need to bring or purchase chairs once you get here. We are providing tents and we are providing tables for all the teams, so you don't have to worry about those. But if you want to sit anywhere on the ground, you need to bring your own chairs. There's plenty of places where you can buy them inexpensively in Las Cruces, unless you want to, purchase them and then bring them over to the States. That's up to you.
Okay.
Yeah, but you'll need that. As a reminder, the Border Patrol has a immigration checkpoint in between Las Cruces and the Spaceport, so you will have to have your appropriate ID with you going through that checkpoint. The Border Patrol is used to this event. They know that they're not going to hassle you or anything, but just make sure you have your IDs with you. Visa stand. One of the reasons that we're doing this and trying to get a look at the rocket a month out from the competition is that in the past we've had occasional issues with teams arriving with their rockets essentially unbuilt and then spending their time in their hotel rooms or Airbnb painting their rocket, epoxying the fins on, which tends to make a mess, which tends to make the owners of the hotel or Airbnb very unhappy. So do not be planning to be doing major construction while you're here. We want to see that all done before you leave for here, with the obvious exception of getting your motor once you're on site.
Okay.
Yeah. And I think we've got pretty much everything done as far as I'm concerned. You're right now, everything you've shown me looks really good. You're a strong team. You've got your act together. Let's like I said, we'll set up about a 15-minute call so you can show me your rocket on the 19th. But should give you enough time to get it largely done Because that's, you know, that's kind of a go, no go criteria for us right now. Okay,
Okay,
so
yes, I'll email you about the meeting on the
Yeah.
19th.
yeah, you know, and I'll give you some availability, some a couple windows that we can use so that, you know, we'll figure it out.
Yeah,
Okay, okay.
Okay.
Does anybody have any questions for me?
not from us. We got pretty much everything. Thank you.
Okay, so, you know, it's a competition, but it's also, you know, a chance to, you know, be safe, to have fun and get to meet your fellow Rocketeers from all over the world. I'm really looking forward to meeting, or in some cases, re-meeting some of you. And I'll be taking care of the post-flight data recovery. So you will see me in the recovery tent when you recover your rocket. Okay. All right. Well, if that's all I have. I've seen everything that I can see right now. And like I said, we'll circle back on the 19th to see your rocket assembled. But other than that, I have nothing else for you right now. You all have done a good job, and I look forward to seeing your actual rocket in a 10 days or so.
Okay.
Okay, very good. Thank you very much. I know it's tough as a student to have to get up quite so early. So I appreciate you being able to handle this review at this point.
Okay.
Okay.
Thank
All
you
right.
so
Well,
much.
thank you very much. You have a great rest of the day, and I will talk to you on the 19th.
Okay.
All right, thanks. See you.
Okay, you're welcome. Yeah, take care.
Thank you. Thank you.
Thank you, Julian. Thank you, Dan, and thank you, Tansu.
Good night, everyone.
Hi, Julian. Good morning.
Hey, how are you?
I'm doing well here.
Good.
Got back from a week in Puerto Vallarta, having nice people bring me cold drinks on the beach. So, so I'm feeling pretty mellow right now.
Hey, that's a rocket.
Morning, Bill and Julian. Maybe an afternoon for you.
Right. Yeah. Yeah. Good evening. Yeah. Glad we could work it out. And I see a rocket. This is good.
Yes. So, welcome.
So yeah, so this is our full rocket assembly. And do you want to see like any components closed up?
Yeah. Why don't you just start at the nose and just point out the key features as you go. We'll go all the way nose to tail.
Sure.
And then I'll take care of it.
Okay, sure.
So we probably present to you the series of the Cursor 3 rockets. And basically there's mainly five parts depending on how you count it. So firstly here we have, So firstly here we have a nose case section made out of carbon fiber. This is where we're going to put our payload inside.
Okay.
Attached to the second section, the main parachute section via coupler. And again, connected to the avionics bay. So basically the control system, sensors, etiquette. Then behind the avionics bay, there will be the drogue chute section. So basically the main parachute and the drogue parachute will have its own respect compartment for itself. So this side is drogue. And finally,
and yeah, just real quick, and you're using nylon shear pins, I assume, to for your separation points.
Pardon?
Are you using nylon shear pins for your separation points?
Yes.
Held together until the charges fire. Okay.
That's all. Probably there will be a charge. There will be a shear pin here, but not yet. And then there's the booster section, our powerhouse here, which is basically made of carbon fiber. This one is, the rest of it was made with fiberglass because we want the radios from the avionics bay to come out, but with carbon fiber is kind of stronger. So, and we don't really need the radio transparency here, so we just kind of use carbon fibers here. And then at the end, you see here is the fin, and we have our new hybrid OGIF. What is called? Hybrid OGIF. OGIF. What is called? Tail cone here. Yes.
Boat tail. Yeah.
Boat tail.
Okay.
This is like
and and let me just point the camera back at the fin can for a second here.
Please.
All right. And so you've got that through the wall and then riveted, and those go attached into the stringers of your fin can. Am I correct?
Yeah. So basically, the bracket will be inserted inside. So how the fin is that not from like fiberglass epoxy outside. We just put some like brackets inside, and then we screw the fins in, so like kind of reduce the aerodynamic drags.
Okay. And are you going to leave it that way, or are you going to do fillets over the top of that?
Fillet.
Can you repeat your question again?
Yeah. So are you going to basically just fly it that way with the the attachment showing with the screws in it, or are you going to do a fillet there to smooth that transition?
We're just gonna fly with it with a screw in.
Okay.
But
okay, good.
I hate screw with it.
All right. Okay, press on.
Okay, so let's start in detail. So I will start in detail. Firstly is our boat tail section. So this boat tail section was actually our new idea. The last time we didn't have it. It will reduce the aerodynamic drag from the pressure difference from the top of the rockets and the bottom of the rockets. And in this,
design, we designed it to be a hybrid model. So basically, in the initial part here, we have the tangent ogre section profile, and then afterwards we will have a conical profile. Because we want it to be a full conical, but the inside we want it to also hold the thrust plate inside too, so that it can take the forces of the motor.
Okay.
And if you look closely, you can see this iron ring here, aluminum ring here. This is our thrust plate. So
Okay.
It's basically where we are going to put our motor block, where our thrust will be. And the thing is that the outside of the thrust plate will just align directly with the airframe and the boat tail. So it basically kind of makes like one single profile instead of like, some ridge or something like that. So it will be more efficient.
Okay.
It also is better at, aligning. It makes it very easy to assemble too.
All right.
So
Okay.
Yes.
Go ahead. Keep going.
Okay, so that is the fin. We have already talked about that, but basically, bracket inside, we put the fin in between, screw it up, and then it's ready for launch.
Okay.
And then the inside of our booster section here, there will be a motor suit, a paper motor suit, right? A paper motor suit that kind of aligns. Let me show it to you. Okay. So basically this thing. So as you know, the mortars usually doesn't have the same diameter as our airframe. So we have this basically a cardboard that help us align with the rockets and the mortars, so it doesn't go like spinning or go haywire in mid-flight.
Right.
And this thing is like basically
the centering.
Yeah, this part is like a 3D printed centering block. So it's like when you insert it inside, you kind of like these things help align it like directly.
It also aligns the brackets in place as well.
So as you can, there is a ridge here, which holds the fin when we insert it inside with the L bracket.
Yeah. So if you look in this way, you could see that it's not perfectly round because this section is where the fin bracket will be. The fin bracket will be here, and then the fin that we said we're going to insert directly will be sitting just in between the bracket. So that's the reason for this shape.
Okay. So you've got that 3D printed. What did you use? What type of filament did you use?
ABS.
Okay.
Last year we used the ABS and it is completely fine. So this year we will also use ABS for this one.
Okay. No, it's a good choice.
It's not the main load receiving force, but yeah, ABS is probably stronger than PLA or other filaments. So here's that. And then the connection between the booster section and the drogue parachute section, basically we have like a
Okay, before we move on, can you show me where your rail buttons are going to be and how you're attaching them to the to your rocket?
Okay, so there will be two main rail buttons, COTS rail buttons. The first one will be around here, which is at the CG of the rocket, and the second one will be at the aft end around here.
Okay, and so are you tying those into centering rings, or are you using something else to anchor those rail buttons onto your airframe?
Using screws, just screw it on to the airframe.
Screw it to the airframe.
Okay. Okay, and when you screw it through the airframe, do you have like some kind of like a little shim or spacer to where the screw can seat through, so you're not just so that the carbon fiber airframe isn't the only thing that's holding that screw on?
Yep.
We have that inside the bracket, like the fin bracket. We have the thread inside, so we just screw into the fin bracket, not the airframe.
Okay, good. All right. Okay, keep going.
Okay, so basically inside here will be another bulkhead just for safety measures. So if there's like more forces coming through the air from the booster section on the top, the forces will come through this bulkhead. So basically it's like a flat disc that helps receiving the load from the thrusters. And then this part you see is hollow part will be where we're going to put our drogue parachute. This is where we're going to deploy first. So nothing fancy here. There's going to be a couple of here just to connect it. I believe there's shear pin too. Yes, there's going to be shear pin. We haven't drilled it, but we haven't drilled it. A shear pin over here, and then we're using gunpowder, CO2.
We're using both SRAT and COTS for the redundance. The first one is the COTS, which we'll be using Eagle, and the second one is SRAT, which is a thing called Dodo. This is one of the components.
Right, yeah. Yeah, no, I remember that from your presentation earlier. Yeah, very nice piece of engineering, gentlemen.
Oh, thank you. And yep, so this will be the grow part, the grow compartment, and this will be the AV bay, the avionics bay. Do you want to see inside our AV bay?
Yeah, yeah, just real quick. I mean, if you can pull it apart.
So this will be our avionics. So the computers, the flight comm, and the each sensors are in manufacturing, and which is already underway. So no worries about that. And our camera will be out from here, and there will be the camera shroud too, which is a forged carbon fiber.
So basically what we are doing, what we're trying to achieve here is that we want to have like a look capability. So like you want to see the fin and the ground when we launch the rocket. So what we're going to do is that you're going to create a model like something coming out, and the shape that comes out like cloud and protects the cameras again. And then we're going to insert the camera so that it can look directly down from the rockets.
All right.
Yep, so this will be the view of the camera shroud. And this is the forged carbon fiber that we have done.
Oh,
there will
nice.
be at least 2 on the rocket and some more for the spare.
No, nicely done. Yeah. And what did you use you're using ABS for your for the 3D printed parts of your avionics bay?
Yes.
Yeah, everything is ABS. Everything is.
Okay. All right.
And the next part will be our main compartment, which is the main parachute. And it will be ejected about 400 feet before landing. This is the main, and also this is where the COTS and SRAT ejection system will be. And the next one will be our bulkhead around here from the coupler from the nose cone. And yep, the rest is the nose cone, and the payload will be inside.
Okay. All right. And your payload is attached. Is that correct?
Yeah, it is the gimbal.
Oh yeah, right. Okay, got it. Yeah. Sorry, I've done 4 other reviews today, so I get
Okay, we understand.
right. And your okay, keep going. I'll remember what I was going to ask you here in just a second.
So we have this aluminum tip here too. At first, it doesn't, kind of fix with the nose cone because we don't have any payload inside. But
Right.
We're gonna attach to the payload, and then the weight of the payload kind of like, stitch it up.
Also, there will be multiple bulkheads inside, and we will attach it with the A stud.
Yes, so basically, and so basically, when we assemble the payload inside the nose cone, there'll be like a stud that run through and connect to the payload, and at the bottom there'll be another bulkhead which will compress the nose cone tip and the bulkhead together, so it's secured tightly.
Okay. Okay, I remember what I was going to ask you here. The switches, what kind of switches are you going to use to arm and disarm your systems?
It will be a switch in the AV bay from the outside. It will be a key switch. Turnkey.
Okay, using key switches, rotary switches.
Yep, a turnkey.
Okay. Okay, that's good. All right. Well, I told you this would be quick. Rocket is looking really good. Pretty much answered all my questions. I've seen what I needed to see myself. Jillian, do you have any comments or questions for the team?
Not at all. I'm sure they'll do great.
Okay, and now it's looking good. All right, gentlemen. Thank you very much for taking the time to re-attack with me. Yeah, please make sure you send this piece of the recording to the Ezra email. And as far, like I said, you've answered all my questions, satisfied any issues I have. So I'm going to look forward to seeing this baby fly in a month.
Thank you. Thank you.
Okay, thank you. You're welcome. Have a good rest of the day, and we will and I'll see you in New Mexico.
Have a good night too. Thank you.
Okay, excellent.
Excuse me,
Okay,
I have
take care. Thank you.
recorded video. So when we submit the video, do we submit by replying the email that you have sent us for arranging the Zoom call?
It's the let's see, the yeah, you can send it to me and then make sure you send it to general.info@ezrarocket.org.
General.info. Okay.
@ezrarocket.org. And I assumed you already sent the first part, but if you didn't send the part from when we did the earlier review, if you could just combine those together, just send them both together.
Okay, sure.
All right.
We will. Okay.
Perfect. Okay. Any other questions or concerns?
No, but thank you for the time.
Okay, thank you for being able to come and show me your rocket. Okay, appreciate it. Have a good evening.
Thank you very much. See you in
Yeah,
Mexico.
bye-bye.
Bye-bye.
Thank you. Bye-bye. Have a good night.